Hello, Chem 1B. This is Chapter 17, Lecture Video 9, our last Chapter 17 lecture video. And in this chapter, we're going to start off by talking about selective precipitation. So I kind of mentioned this earlier in a previous video, but one of the things we can do with solubilities is we can selectively get rid of certain ions from a solution. Let's say my drinking water has a lot of lead in it. That's really bad, right? I want to get rid of the lead. Well, I can find an ion that will have a really low solubility with lead and add it to the solution. Maybe I want to keep the sodium in the solution. Good, though. I want that sodium in my water for whatever reason. Well, sodium probably won't precipitate out because it's very soluble with most ions. So I can selectively precipitate out the lead while keeping the sodium ion and possibly other ions present in the solution. So how do we do this? Well, let's look at copper and silver, right? Silver ion and copper ion. What if I have a solution with both of them in it? Well, maybe I want to just get rid of the silver while keeping as much of the Cu plus in solution as possible, right? Well, I got to pick an anion that will precipitate out the silver before I see any copper precipitating out. And one of those such anions could be chloride, right? Silver chloride has a KSP of 1.8 times 10 to the negative 10, while copper chloride, copper 1 chloride, has a KSP of 10 to the negative 7. Because this value here for copper is so much larger by almost a factor of 1,000, then AgCl's value, the AgCl is definitely going to precipitate out first. And I can probably get rid of most of the Ag plus before I start losing too much copper in the system. So again, why does AgCl precipitate out first? Well, it's because of this really small KSP in comparison to the KSP for copper 1 chloride. So this is known as selective precipitation. So let's do a problem involving this. We're going to use the same situation, right? So everything here is going to be on the next slide. So, sorry, we'll do that on the next slide. Selective precipitation, right? It's very useful. The way it works is by using QSP and KSP. So for instance, in this example, we have these two chloride species. We can calculate when one will precipitate while the other one stays in solution. We could calculate how much of one ion is left in solution once the other one starts to precipitate. So there's a lot of useful values here that we can calculate. So let's do a problem. So if we have a solution that contains 0.5 molar Ag plus and Cu plus, and we're adding 0.5 molar HCl, what concentration of Ag plus will be left in solution when CuCl starts to precipitate? Okay, well, I know that QSP is going to be basically equal to KSP when CuCl starts to precipitate. So specifically, the QSP for CuCl will be equal to the KSP for CuCl when CuCl first starts to precipitate. So if we think about that, right, I know my Q value here is 0.50 molar for copper plus ion. What I really need to figure out here is what's the concentration of Cl minus that I need to have in order for these two to be equal, right? So I go, okay, well, QSP is equal to, because my equilibrium CuCl solid goes to Cu plus Cl minus, both aqueous. Well, I know QSP is going to be equal to the copper plus concentration times the Cl minus concentration. And at this point in the system, QSP needs to be equal to KSP because that's when it will first start precipitating. So I know the KSP of CuCl is 1.7 times 10 to the negative 7. And this is going to be equal to my copper concentration, which initially is 0.5 molar, times the chloride concentration. So I can divide this over and get what concentration of Cl I need to have present in solution for copper chloride, copper 1 chloride, to start precipitating. It's going to be 3.4 times 10 to the negative 7 molar. So pretty low concentration. At this point, I can then calculate what concentration of Ag plus will be present, because if I have this concentration of Cl minus, and I know KSP is equal to the concentration of Ag plus times the concentration of Cl minus, because, you know, AgCl goes to Ag plus Cl minus here. Solid, aqueous. Well, I can just kind of plug this in here. I have KSP, and I can solve for my Ag plus concentration to get what concentration of Ag plus I have as soon as copper 1 chloride precipitates. So I know that it's 1.8 times 10 to the negative 10 is my KSP. This is equal to my Ag plus concentration times 0.34 times 10 to the negative 7 molar. And I can just divide over and get my Ag plus concentration. And this gives me that I have now 5.29 times 10 to the negative 4 molar Ag plus is present in solution. So we've really decreased that Ag plus concentration significantly. Now, we were also asked what volume of HCl would be required to get this to happen. Well, I know that for every HCl I add, I get Cl minus at the same rate. For 1 milliliter, for 1 mole of HCl, I get 1 mole of Cl minus. Now, in order to actually do this, I keep meaning to add here that let's say the volume of my solution here is 500 milliliters, because I need that value in order to calculate this answer. So I know if I have 500 milliliters, this means that I have 0.500 liters. And if I have 3.4 times 10 to the negative 7 molar HCl or Cl minus, if I multiply this by 0.5 liters, I get how many moles of Cl minus I have. This gives me 1.7 times 10 to the negative 7 moles of Cl minus. I can now take my molarity of HCl that we were given is 0.5 molar and get how many liters of HCl I would have needed to add to get this number of moles present in the system, right? So if we divide this, right, this is moles of HCl, and HCl and Cl are 1-to-1 per liter. Moles cancel here, and we're going to get liters of our solution, which is about 3.4 times 10 to the negative 7 liters, or, times 1,000 there to get milliliters. 0.00034 milliliters. So we barely have to add even a little piece of a drop here to get this thing to that concentration. Okay, so if you have any questions, please let me know. Let's move on. All right, so complex ion equilibrium. One of the things you need to know about is what is a complex ion. Now, a complex ion is an ion that is complex. Ha ha ha. Not really. It's an ion where we have a metal center and a ligand or a compound bound to the metal center as a Lewis base. So effectively our metal here is a Lewis acid and the NH3 here is a Lewis base. We're donating a lone pair to the Ag to form what we call a coordinate covalent bond. Now we're going to talk a lot more about complex ions in chapter 22. But effectively, it's not so much a polyatomic ion. I mean, it is multiple atoms in the ion for sure. But it generally has a metal present, and then some either ion or neutral species is attached to the metal, and we have an overall charge. The charge can be either positive or negative, depending on what complex ion we're talking about. Obviously, this one's positively charged. And these guys have equilibriums too. So we're going to talk about a new type of equilibrium constant in the last one we cover in this class. And it's known as a formation constant, or a Kf value. Now, Kf values are for the formation of complex ions like this AgNH3 complex. And they're equilibrium constants, so it's the same deal as always. Products over reactants, concentrations taken to the power of whatever the stoichiometric coefficient in the balanced equation is. Now, one thing you should know about KF values is they're huge, really large things. They're kind of like the opposite of KSPs. KSPs are really tiny. KF values can get upwards to the power of 10 to the 33, positive 33, right? So huge values. Now, these can affect solubility of ions. So if we have like an ionic compound that's not very soluble, but can form a complex ion, we can have really increased solubility under certain conditions. So let's look at that side of things. Let's look at AgCl again. AgCl, like I said earlier, is a really insoluble compound. It has a KSP of 10 to the negative 10, so it's a really small KSP, very heavily reactant favored according to our equilibrium. But Ag plus, I should have a plus here, Ag plus can form a complex ion with ammonia, NH3. This is our complex ion. And the KF value there is about 11 million is the size of it, right? So again, really big value here, 10 to the 7. That's huge. Now, this actually can affect the solubility of AgCl, right? If we look at AgCl's KSP equilibrium, it looks like this. I don't know why I went backwards there, but AgCl breaks down into Ag plus and Cl minus. Now, if I add NH3 to a solution containing AgCl, what's going to happen? Well, according to Le Chatelier's principle, if I add this guy, this is going to shift towards the products really hard because of this KF value, to the point where all of the Ag plus in the solution is going to get used up pretty much. It's going to go way down. Well, if we look at our solubility equilibrium, if Ag plus's concentration goes down, what's going to happen to this equilibrium? Well, it's going to shift towards the product side, i.e. AgCl will dissolve more. This is going to increase the solubility of our AgCl in solution dramatically. So if I try to dissolve AgCl in the presence of NH3, I'm going to get a really soluble compound. It's going to dissolve really well in that solution. Whereas generally, if I just dissolved AgCl in pure water, I don't get very good solubility. So there are like hundreds of different complex ions out there. I need you to know about 3 of them for this chapter and this upcoming test. And these are the 3. So we have iron 2 plus with cyanide, 6 of them. Charge is important. So you should know this formula, and you should know that when we have iron 2 plus and cyanide in a solution, we form this complex ion. The same thing can be said for silver and cyanide and silver and ammonia, just like we saw up here. Now you should also be able to write out the equilibrium for these 3 for sure, and then any other ones I provide you, right? So if I provide you the formula for a complex ion, I expect you to be able to write out an equilibrium for that complex ion. Now, how do we do that? Well, it's pretty simple. We work backwards, right? Like you saw here with Ag and ammonia, we put the complex ion on the product side. And then how do we make this from these 2 things separately? Well, we have Ag here, and we have 2 NH3s there because of this 2 here. So if we were going to do this for this guy here, right, the iron cyanide compound, right, I would start with that as a product. So FeCN6 to the power of 4. Usually we put brackets around it, but we'll just say 4 minus there. This is aqueous. That's my product. Now on the other side, I need to figure out what the charge on iron is in this. Well, cyanide is -1 each. There's 6 of them. What plus -6 gives me -4? Well, it has to be 2 plus, right? So I have 2 plus Fe, and then I have Cn minus here, aqueous, and I have 6 of them. And this is my balanced equilibrium. So you should be able to do this for the other ones as well. All right, so let's do one last type of problem involving this. What is the equilibrium constant for the process of dissolving AgI in a solution of NaCN, right? The KSP for AgI is 8.5 times 10 to the negative 17. And the Kf value for AgCN, the complex ion, is 1.3 times 10 to the 21. Well, as we know, right, we can write out these 2 equilibriums. AgI solid KSP equilibrium is this, right? We have Ag plus as a product and we have I minus as a product. And this is our KSP equilibrium. Now, if we look at the complex ion formation, let's use a different color here. We have AgCN2 minus 1 aqueous, and that's formed from Ag plus aqueous and Cn minus aqueous, but 2 Cn minuses. And this is our Kf value. Now, if we want to figure out what's going on here, we have to combine these two equilibriums into one equilibrium, right? Well, how do we do that? Well, we're going to add them. Now, if I add these two, you see that there's one thing that does cancel, right? The Ag plus cancels out here. Everything else stays in the expression. So what we end up with is AgI solid plus 2Cn minus aqueous goes to AgCN2 minus aqueous plus I minus aqueous. Now, the K value here, because we added the two, has to be equal to the KSP times the Kf value, right? Or in this case, 8.5 times 10 to the negative 17 times 1.3 times 10 to the 21. This gives us a value of about 1.05 times 10 to the positive 5 is my Kf, or my new equilibrium constant here. All right, so if you have any questions, please let me know. Discussion sessions or email are the best way to reach me.